Okay, so welcome back everybody to the second day of the course. So the first thing, yesterday I mentioned, some people asked me after the course to give references for the material I covered and I will cover, and I want to do that. So for the random graph part on GNP, so for the GNP part and for the given degree sequence, there's 3 books with exactly the same title. There's a book with the title Random Graphs by the most recent one, which you can find online, by Alan Fries and Michał Karonsky. Then another one by Svante Jansson, Tomasz Buczak, Andrzej Ruczyński, and another one by Bela Bolobash, with all exactly the same title. And then there's another one which is called Random Graphs and Complex Networks, by Remco van der Hofstad. And for the part on random geometry graphs that I mentioned, and I will go in more detail now, there's a book by Mitsche Penrose with exactly this title. And there is also a survey containing most of the ideas by Mark Walters. Okay, so these are the references that I forgot to write, and that are at least for the course of yesterday, today, and tomorrow. And yesterday I mentioned a theorem which I didn't prove, but which I will prove now, namely about random geometric graphs. So I recall the setup, and I will slightly change the setup to simplify the proofs. So first, yesterday I said that the model of random geometric graphs is given by n uniform points on a unit square. So just for not carrying around my factor n all the time, I will consider now a square of side length n. This doesn't matter. This is just because otherwise I will forget the factor all the time. And the second thing, instead of working with n uniform points, we'll consider here a Poisson point process of intensity 1. So we'll make a Poisson point process inside the square of intensity 1. And then you can see that this easily can be done on the entire plane as well, but we'll look at the finite version. So that means that whenever I take a set A here, then the probability that A has exactly, let's call this process chi here, has exactly k points, is exactly the probability that the Poisson random variable with intensity equal to the area of A is k. Okay. That's one thing. And the second thing, for if you have these joint areas, so if I have A1 here, A2, A3, if you have these joint areas, then they are independent. So the probability that for all A1 and so on disjoint, the probability that A1 contains K1 points, A2 K2, A3, this is an eta here. The eta is K3 and so on. This is just the product of these probabilities. Okay, so that's the setting in which proofs are usually easier, because one disadvantage of the uniform model is if, for example, I tell you that A1 contains already n points, then the probability to have one single point or more in A2 is exactly 0. And that's complicating.
Sorry, keep saying it.
I'm saying yesterday we had a square where we threw in n uniform points. For each point you choose an x coordinate uniformly in the 0, 1 interval and the y coordinate uniformly in the 0, 1 interval to get exactly n points. Now I'm not doing this, so this Poisson point process has on average n points, and the probability to have exactly n points is of the order 1 over root n, basically. But the advantage of this is that if I'm telling you something about A1, this doesn't tell you anything about A2. If I were in the uniform model and I'm telling you this A1 has already n points, then I know I must have 0 points in here. So I don't have the desired independence.
So we are changing models, right?
We're changing models, but most of the results that you can prove in this model, you can actually de-Poissonize. So what does that mean? If you prove something in that model that holds with a probability that is tending to 1 sufficiently fast, say faster than 1 minus 1 over root n, then you can transfer this result directly to the uniform model, because the important property of this process, if I'm telling you conditional under having exactly n points, the distribution of the points is exactly as the uniform distribution. Okay? So sometimes it's harder to de-Poissonize, but the easiest thing is when you get an error probability that is smaller than 1 over root n, then since 1 over root n is basically, as I said, the probability to get exactly n points here, then you can transfer a result holding asymptotically almost truly here also to the uniform model. The advantage here is that the calculations are much easier thanks to this mentioned independence. Okay? And the theorem I mentioned but didn't prove yesterday was the following. So we're having, let me call still the model G and R. This is my Poisson point process. The theorem was, so let pi be a Poisson point process of intensity 1 in the square S of area n centered at the origin, and G be the associated random geometric graph. Be the associated random geometric graph, which means that the points of the association is just that the points of those vertex set are exactly the point of the Poisson point process, not exactly n, but roughly n on average. And I connect 2 points if their Euclidean distance is r. Observe that I will not divide r now by n because we have now an area of n. Well, then we say that Rn star, which is now root log n over pi, so no more, everything, all lengths are scaled by a factor root n, is the sharp threshold for the property of being connected. Is the sharp threshold for G being connected. Okay, so that was the theorem I mentioned in the non-Poisson setting yesterday. And I will try to prove this, since some people asked me about this yesterday. The first part of the theorem is easy. That's the part I mentioned yesterday. So if R star part 1 is the easy part, if R less or Rn less or equal than 1 minus epsilon Rn star, well then I said that AAS asymptotically almost surely, and actually I should aim for something stronger, but I will not do this now. So I should get something that holds with probability 1 minus something small than 1 over root n, so that I can then easily depoissonize and transfer it back to the uniform model, but which is not problematic. But let me not do it now. Let's just focus on this model, which itself is perhaps even more natural for probabilists. If Rn is less or equal than 1 minus epsilon Rn star for any positive epsilon, then AAS, there exists isolated vertices. So that was and I will just sketch this because if I call x the random variable of the number of isolated vertices, well then what is E of x? Well, here is my square, and as I said yesterday, if a point is isolated, if everything in this ball of radius r around the point is empty, so the area is r squared pi. I have a Poisson point process of intensity 1. The probability that this Poisson point process is 0 is exactly e to the minus the area. So that's the probability that this, for a fixed center here, this ball is empty, and we have n points here on average. I'm cheating here a bit because the number of points here is a random variable, but using Mecke's formula you can make this formal, and you can see that if you plug in r this number here, okay, then this expectation here is exactly 1, right? You get e to the minus log n, which is 1 over n times this n here. This is 1. And if we are a bit below, well, then you get here e to the minus 1 minus epsilon here. So you get an n to the epsilon here, and then you make a second moment, and that shows that there will be isolated vertices, right? By a second moment method, AAS isolated vertices. So there are two points where I cheated first. Well, this is not exactly n here. The second point, which is also not completely correct, is okay, if you're at points that are closer, that are relatively close to the boundary, say those here that are a distance at most r from the boundary, then it's not true. Then it's not true that a full ball has to be empty, right? What has to be empty is rather something like, yeah, just a part of the ball, right? But you can do the calculations. Believe me, this for now, that there is less space that has to be empty here, which is bad on the one hand, and which would be easier to get isolated vertices. But on the other hand, the area that you have here is also much smaller. So the number of points you will have will not be more than this. You have to do this carefully. So you get these points for everything inside, and for all the points in here, well, you have to put here an r squared pi over 2, for example, or an r squared pi over 4, for example, if you're right at the corner. But there are much less points, so you don't have n. You just have as many points as here in the annulus, or in this small rectangle here. And then do a second moment. It's a bit of calculation, but it's not difficult. Okay? So this means that if you're below this threshold of connectivity, well then for sure you'll have, or with high probability, asymptotically almost surely you will have isolated vertices, and therefore for such radius the graph will not be connected. Okay? Now the part 2 is a bit harder. So we want that if Rn is larger than 1 plus epsilon Rn star, then AAS G connected and just the fact to have 0 isolated vertices as in the GNP case does not show this. And the same proof technique as we did in GNP does not work here. So we have to do something else. One can get a simpler result. First, so before proving this result, let me first make a simpler result. So this is not yet the proof of the theorem, but it's just some much easier proof for a weaker result. So a simpler result says, okay, for C large enough, and R being this constant C times root log n, so not 1 over root pi, but just large enough constant times root log n, G is AAS connected. So G and R is AAS connected. This is simple to show. And how do you do that? Well, that's the most basic idea that is used in proofs of random geometric graphs. You just take your square and you tessellate it, you partition it into cells. So that's one cell here. That's one cell, which is such that any 2 points in the same cell or in 2 adjacent cells are connected. So if, for example, if I choose this R over root 5, if I choose this cell size here, R over root 5, well, then I know that if I take any 2 points which are in either the same cell or in 2 cells that are horizontally or vertically connected, then they will be connected by an edge. Because the worst that can happen is if I have here my point x and here my point y, then this is the Euclidean distance between them, and this is at most r. Right? Okay? So then observe just whenever the following happens, that I have at least one point in each cell, then the whole graph is connected. Right? So if at least, observe, if there exists at least one point in each cell, G is connected. And the probability that there exists an empty cell is by union bound just the number of cells. Okay, what's the area? The total area is n divided by one cell size, which is r squared over 5 in area. And the probability that one cell is empty is just e to the minus the area, e to the minus r squared over 5. And you can see that if r is a large enough constant times root log n, then this tends to 0, right? Because then this c here in the exponent kills the leading n there. Okay? So this is a useful technique for random geometric graphs, to just partition or to tessellate, to divide into cells of area or of side length roughly the radius. And this shows that for a large enough constant times root log n, you're connected. Okay, so let's now prove the second part. So that was just an, so to say, a warm-up. If we want to get the desired result that really at 1 plus epsilon times this threshold we don't have a disconnected graph, well then we will do it in 2 steps. And we will need the following lemma 1, which says that take any, let C be any positive constant, and AAS, the graph Gn C root log n, does not contain 2 components of large diameter, so of diameter at least C log n for some C large enough, which might depend on C, but it's a constant. So diameter means if I have a component here, diameter means Euclidean diameter. For example, if this is my component, then this would be the maximum Euclidean diameter, for example, between these 2 points here. And this is the diameter. The maximum Euclidean distance between 2 vertices of the component. Well, and the idea is the following. If I have my first component here, this is large, and I have a second component, this is also large. well then what has to happen such that this is a component? Well, it has to happen that a certain tube, a certain area around this component has to be empty. Right? So some area, something like this, like some tube around this, something like this, has to be empty. Because if I had a point in here, it would connect to this component. And that's unlikely to happen because if the components are both large, well then the boundary around these components is also relatively large. And it's unlikely that you have large connected areas which do not contain any point. Okay. There are a few small details that we have to take into account, and we'll proof of the lemma first. Proof of the lemma. Okay, let's tessellate again. Tessellate again the square into cells of side length. Well, it will be not r over root 5, but it's r over root 20 now. You'll see why. Okay. And the first observation is that each component of, observe, each component of diameter at least C log n has to hit, so to say, either by a vertex or by an edge, by a vertex or an edge, by a vertex or by an edge, at least C log n over r over root 20 many cells. What does hit mean? Well, hit means if I have, for example, my component like this, and this is my tessellation, and then this cell here, this is also hit. So this is a cell hit by a vertex. This is another cell hit by a vertex, and this one, suppose they are connected. Okay, then these cells here is also hit. Yeah, so this cell, a cell which is such that the straight line between 2 points goes through that cell is also hit. That's what hit means here. Right? Because this is just the fact, okay, if you start at this point and you go to this point, well, if this distance is at least C log n, just by pigeonhole principle, okay, every time you travel more than r over root 20, you'll change cells. And also observe as before, any 2 points, the maximal distance in vertices for vertices in adjacent cells is at most r over 2. For vertices in vertically or horizontally adjacent cells, is at most r over 2. So this is the same argument as here. So this distance here is at most r over 2 because this is now r over root 20. And now, define U bar, or U tilde rather, the cells that are hit by a vertex or by an edge, by a component U. And let delta of U bar be the outer boundary of the outer boundary cells of U. So this is a small technical issue, but imagine you have a component which is like this, which is somewhere something like this, for example. Imagine that's your U. Well then, when tessellating it, okay, the cells that belong to you, that are hit by you, would be those ones here. This is U tilde, U tilde, U tilde, U tilde, U tilde, and so on. Then you see that the boundary in general, the boundary does not have to be connected, right? So there could be a hole in here. So this is also the outer boundary. So the boundary of U would also contain this part here, right? So there's a hole inside this component. And there's the other, this is the inner boundary, which I erase here, but I'm just saying that if I just take the boundary, it's not necessarily connected. So the outer boundary cells are all those cells here that are adjacent to a cell in U, but from the outside here as well. And observe that these have to be empty. Right? So observe that observe cells of the outer boundaries of U have to be empty. Well, it's basically the same argument, a bit different, because cells could also be hit by an edge. So for example, if I have my component U here, if this is my component here, and they say another component V somewhere, this is my component V, well then what can happen? Well, the minimal distance between two components, it could either be attained at one vertex here and at one vertex here, or it could be attained between a vertex and an edge. So here, for example, in this case, this is the minimal distance between U and V. In this case, it's between a vertex of U and an edge of V. But if this were less than R over 2, if this were less than R over 2, well then somewhere from this edge, the closer one of these, say in this case this one, would also be less than R over 2. And then the edge from that vertex to that vertex would exist. Right? So since this distance therefore has to be larger than r over 2, and we know that any 2 points by the previous observation in adjacent cells are a distance r over 2, they have to be empty. Right? So there cannot be any point, or there cannot be any point in here. That has to be empty. Because if there were a point, and this one, for example, would be hit by an edge, then this distance between these 2 points would be smaller than r, and it would merge, and it would not be a connected component. Okay? 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 If we consider, as I said before, if we consider the whole boundary, not just the outer boundary, but also this inner boundary, then we said, okay, this boundary doesn't have to be connected. But if we had such a ring or some component which has certain holes, we could just always fill up those holes and consider the outer boundary only. And, well, that's a topological fact that the outer boundary consider the outer boundary only. Let me just write observation. Observation. The outer boundary is diagonally connected. So there is, again, I'm cheating a bit here. First, what does diagonally connected mean? Okay. By the picture here is, if I'm saying that this vertex is also connected to this vertex, then that's what I mean diagonally connected, or star connected sometimes. So here in this picture, these red cells here, they are diagonally connected. Okay. It could not, the only thing that what could happen if we're in a, so this is a fact that is true in the plane. In the square, of course, it could happen that there's the boundary of the square here, right? So it could happen that the square ends at this point, and you have one point here and one point and another set here, and in that case, you just take that part that is, since the component is small, take that part which is not hit by the boundary. So there will be one part inside the square which is at least, say, 1/4 of the whole outer boundary. Okay, so when I say here diagonally connected, this is true in the whole plane. But if you're bound to be inside the area, inside the square of area n, well, just take the largest part that is still there and is up to a constant factor, the same as the whole boundary. That's thanks to the fact that well, if we were assuming that there's two components that are so large, then at least one cannot fill up the whole square. Because in principle, if you have one component that fills up, that is of large diameter, it could be so large that the boundary is empty, right? It could fill up the whole square. But if there is two components, at least one of them will not fill up the whole square or almost the whole square. And take this one of diameter at least C log n, and there you can say that there is at least one boundary piece which is large enough. Okay. And then for such a, if we have this observation, well, then we need just an isoperimetric inequality which says that the boundary of a set basically has to be at least, okay, I'll write it more precisely in the square, at least of the order square root of the set, or the square root of the complement, but this is not the whole square minus u. Okay, S is the whole square. But forget about this issue. This is just for taking into account the case when there's one component which is very, very large. But in principle, whenever you have a component that's not filling up everything, its boundary is at least, in 2 dimensions at least, the square root. And now we can count certain lattice animals. So now we know that this boundary is connected. It's at least of certain size. And it will be unlikely to have such a what we call lattice animal, a section from a connected set of cells, a diagonally connected set of cells, like this one here, empty. Okay? So we count now. Now we can count so-called lattice animals of the boundary, corresponding to the boundary. To the boundary. So take a component, for example, that hits S cells. We know that it will hit at least that many cells, but take a component hitting at least S cells. Take a component hitting S cells. Well, we just have to count how many connected cells, how many connected sets of cells containing a fixed cell are there. Containing a fixed cell U are there. And this is sometimes also known as Peierls argument. Well, how do we count? Well, here we have my cell U, say, and then I have a connected set of cells, say this one here, diagonally connected, as I said. If I have a connected set of cells, any connected graph is determined by a spanning tree. So I can find a spanning tree, for example, like this one. Like this one. And now you can traverse the spanning tree around its contour in exactly this way, that you start, say, here, and you traverse it. Yeah, well, maybe take a different color. I follow the spanning tree going here around its contour. And I'm coming back, so traversing the spanning tree with how many edges? Well, if we have S cells here, the spanning tree has S minus 1 edges, so they're using a walk of 2 times S minus 1. Edges. And how many such walks do I have? Well, we said we fix a starting point, and we want to contain a cell. So we start, for example, here. Well, at each point, since we're diagonally connected, we can only go in 8 directions. We can go up, here, 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 or here. So at each point of my cell, I have only 8 chances, at most 8 chances, because some of the cells might already have been previously used in the spanning tree, but at most 8 chances. And when I'm going on my walk, every time I have at most 8 chances. Actually, for the last edge, I have to go back where I came from, so I don't have any chance there anymore. Right? So, but for sure, at each step, at most 8 choices for my construction of the walk, for my walk. So the total number of walks of this length, so the total number of walks containing u and starting at u and going back to u, containing u of length 2s minus 2 and going back to u, is at most 8 times the number of edges, and as I said, the last edge is not free. For the last edge, I have exactly one choice because I have to, when traversing back, the last edge has to go back to u. And these walks, they contain all spanning trees that I could possibly think of, because every spanning tree will be encoded and will correspond to such a walk. Okay, so that means that the probability that there exists a spanning tree of s minus 1 edges rooted at some cell and yielding an empty boundary therefore, by union bound is what? Okay, here I fixed my starting cell u. Okay, the number of cells, let's say it's at most n. It will be roughly n over r, but at most n. For each cell, if I fix s, I said I have at most 8 to the 2s minus 3 walks which contain all spanning trees. And once I have my spanning tree, well, then I said all this outer boundary has to be empty. So if this corresponds to an outer boundary, if this lattice animal that we're counting here corresponds to an outer boundary as here, all of these have to be empty. Each of these cells has area r squared over 20. They're all independent since we're in a Poisson setup. So the probability that one of them is empty is e to the minus r squared over 20, and there are s of them. Okay? And if we plug in s to be this number here, then this tends to 0. So if s is larger than c log n, for C large, then this tends to 0. Okay, so this cannot exist. You cannot have a large enough boundary, which would imply a large connected set of cells, all empty. But this cannot happen, and this means that we cannot have 2 components. As I said, we could have had one. Because if we had only one, then the one component could swallow or could be all over the place, so that the boundary of that component would be very large. But if we have 2, then at least one of the 2 components has to have a boundary for which the isoperimetric inequality gives this term here, and that means we cannot have 2 components of large enough diameter. Okay, the first part of the second part. So that was showing the lemma, which said there is no two big components. Yeah?
I just wanted to ask to make sure about technical details. So the fact that you got rid of what you call the inner boundary is not because it's like in the probabilistic sense it's sort of good to have full boundary, but in the sense of like trying to count those sets of boundaries with a given size.
Yeah.
It is
It's easier to count.
yeah.
Yeah.
So that's why you got rid of that.
Yes.
And another small question is, does this have a high-dimensional
Analog? Yeah. But you have to adapt the isoperimetric inequality. So
Yeah.
basically, where does this root n come from? It comes from the fact that if I take a ball of area n, then the surface area is or the what's the word? The perimeter is root n. So if you're in d dimensions, well then that will be like d minus 1 over d. Yeah, indeed. So counting it's just easier to count, right? So if we have what I want to do at some point, hopefully next week, if you want to allow also long range edges where for example from time to time you have edges going from here to here, then you could have a component that's here and then maybe has nothing and here. Well, then you would have to take into account all these possible starting points of new boundaries, and then the counting becomes more complicated. But here, since there is a large connected piece, you can do the counting easier. Okay. Yeah.
It's a very silly thing, but if on the lower bound of the number of cells that you hit, is it possible that's r over square root of 10 or something? 'Cause
Maybe.
you go over the diagonal.
Yeah, maybe. That could be. Okay. That could be. Yeah. Okay. You should not take every constant with, you should take it with a grain of salt. Okay. Okay. So that's the first part, which shows that there are no too large components. And they said that there is no too large components for any r being of the order any constant root log n. So this C depends on the constant in front of the root log n of the radius. But basically it says that whenever you take a radius r of any constant times root log n, you won't have too large components. Okay? So then what we have to rule out still is the fact that there might be smaller components. Okay, so lemma 2 now I'm taking into account really the R we want to take, namely it says that AAS, the graph G, which is root log n over pi, now let me put a small error term, something like this, for example, here, 1/2 log n over pi. So this is my 1 plus epsilon root log n over pi. Does not have a connected component. With more than one point. But at the same time, Euclidean diameter less than C log n, where the C is exactly this C here. So the first thing is, okay, if this lemma is shown, then the theorem is shown. Because what do we know? Well, first we said, okay, by the first part of the theorem, there will be no isolated vertices if I'm above 1 plus epsilon. Maybe let's make it 1 plus epsilon here, just to make it easier. By the first part of the argument, we said there is no isolated vertices at this point. So what else do we know? We know that there is, by the first lemma, there is no two large components, meaning no two components with diameter larger or equal than C log n. There could be potentially a disconnected graph. How could that happen? Well, it could be that there is a component that is not an isolated vertex, so it has strictly more than one point, but at the same time, it has a small diameter. But if we show this lemma, then we rule out this case as well. So there is no component of this, so there is just one component in total. So, okay, so the lemma, lemma 2 implies the theorem together with what we already had before. So we just need to prove this lemma 2 now. Okay, suppose there exists such a component. H is such a component. Then we make two cases. Case 1, the diameter of H is even much smaller than what we have here. Say it's very small in the sense that it's at most log n squared over root log n. We call this psi. Okay, what does that mean? Well, then I have all my points inside a small area. This is psi here. But R is much larger. R is of the order root log n. So R is like here. This is R. So then this means that I have to have at least 2 points here, at least 2 points here in this area, and all this empty here. So this is, let's say, empty. Okay. But this is very unlikely to happen because you just have a very small area in which you want to have at least 2 points. So in particular, the probability that for a fixed vertex there exists at least one more point in this part here, and 0 points in this part. This is so small, you can do the computation. This is less than 1 over n. So even by taking a union bound over all n possible starting vertices, this will not happen. Yeah? Because it's just, if there is one point, what you get in a Poisson point process, you add artificial, by some so-called pattern theory, you add a point, and then in a very small area close to this vertex, you should find another point, but that's still a Poisson point process, and that's unlikely to happen. If you compute the probability, this will be less or equal, this will be strictly less in order than 1 over n. And then taking union bound over all n vertices, this means that this will not happen. Okay? So this was the first case. And the second case, is when the diameter is larger than this, but still smaller than C log n. Well, then you know your points are somewhere in a component. Imagine there exists such a component. Something like this, say 4 points, something like this. Okay, consider the smallest axis parallel rectangle that contains all these points. Say this one in this case, consider R. And the smallest axis parallel rectangle containing H. Okay. Well, since the diameter is at least chi, one of these two sides, there's again a diagonal here, one of the two sides, okay, now let me put this root 2 here, one of the two sides of the rectangle, say the of the rectangle R is at least chi over root 2. Okay. And then observe that if you have this rectangle, well, then you have to get some extra area empty. So let me draw it. So for example, since this is a point here, this is a point here. Okay, there's a ball of a half ball, say. This is R here. That has to be empty. And say if this is the larger side, this has to be empty. This has to be empty as well. Something like this, maybe. So this would be exactly an area R squared over 2 and an area R squared over 2. But there is still some extra area that you get here. So for example, okay, the picture is maybe, let's say, the height. The picture, say the height is the larger one, which is okay, not the case here in the picture. But if this is larger, that's chi prime. If this is larger than chi prime, then you get a little bit of extra area. Since chi prime is now not so small, chi prime is at least of this order. And you get a little bit of extra area here. So something like here of this point, what you get here empty, something like this, and something like this, which is not yet counted here and not yet counted here. So if the height, for example, okay, this is from the picture, maybe it's almost a square, but if say the height is a bit larger, well, then you get a little bit extra area, a little bit extra area has to be empty of points. So in particular, if this chi prime is at least some constant times R, well, then you get here at least, then this area here is at least another constant times r. Then extra area is at least another constant times r squared. So it's almost, it's a certain fraction of the full ball that you get for free here, which, for example, in this picture, right? If this area is, or if this length here is say 0.1 times r, well, then you get a little bit, then you get, say, 0.01 times r squared extra. And if not, if this is smaller than r, of smaller order, well, then the extra area you get is at least something like this height times r. Yeah, then basically you get here like a, you could think of it as a rectangle here, which is, well, then the picture would be rather like this. Well, this is chi prime, and this is r here. Okay, then extra area is at least of order, say, 2r chi prime. Okay, and these extra areas help you to do the calculations, because you have to get some area now which is empty, which is a bit more than a ball. It's not just r squared here and r squared here, but it's a little bit more here, a little bit more here. And there's not too many choices for this rectangle, because the rectangle is small. So in both cases, we'll not do the calculations now, the probability that such an area is empty is smaller than for a fixed rectangle here. For a fixed rectangle, the probability that this part here, and this part here is empty is, say, smaller than, for example, with these choices, 1 over n times log n cubed. And how many such choices do we have? Well, there are at most n components, because there are n vertices. So how large can the rectangle be? Okay, first the area has to be, okay, the rectangle is fixed. Let me write it. How many such areas are there? Well, at most n choices for the starting vertex of the component, and choices for components. And then this rectangle is of order log n, because we said that the diameter is of this order. So the rectangle is of order log n. So the other vertices are in rectangle of order log n, of order log n. And how many choices do I have? Well, I fixed one vertex, and I have to fix 3 other vertices. Then I know where the rectangle goes. So, for example, if I know this vertex, this was my starting vertex, and this one, and this one, and this one, then my rectangle is determined. So I have at most log n cubed many choices. So at most log n cubed choices for determining the rectangle. Yeah. So first I choose my starting vertex, which is one vertex of the boundary of R, and with those 3 points here that have to be now in an area of log n. So I have log n times log n times log n. I have log n cubed choices. And I take a union bound over this n and this log n cubed here, together with this probability for a small rectangle here, and this tends to 0. Okay. Okay, so that concludes the proof. And I have maybe 30 seconds left, so this is for questions if you. Otherwise, just a comment. So for those of you that still have in mind this tessellation argument that I had, since I didn't present an open problem in the open problem session, here's an open problem that is hard, but there were other open problems that were hard as well, so I don't feel too bad. So if you want to know the question, what is the threshold radius Rn star for having a linear sized component? In a random geometric graph. So a component that has at least, say, constant times n vertices. In the setup we have here with the Poisson point process and with area n, there are only bounds known. It's known that it's at least one constant and it's at most another constant. Physicists, they know what it is. But there's no rigorous proof. It's known that there exists a sharp threshold. There's a general result that for certain, similar to Friedgut's result, that for properties that are monotone increasing, there is a small window in which you have a jump from from not having the property, say, to having the property. But where exactly the threshold is, that's not known. So if someone wants to have a challenging problem, and I think that's a good candidate, yeah?
What's the order of Rn?
The order here?
Yeah.
Constant. That's easy to see. That's easy to see because you can do some, yeah, I didn't explain that, but you can do comparison with certain percolation arguments. For example, you can compare it with bond percolation on Z2, but you will always lose a bit because, well, in Z2 you're connected when the edge is there, say. And if you're above the percolation threshold, then you'll have an infinite component. But of course, here your areas are balls, right? So you might, for example, connect to someone that is just a little bit out. So you can get upper and lower bounds, and you can improve those bounds when you look at a triangular lattice, or depending on the lattice, or look at side percolation instead of bond percolation. But you'll get only bounds. So I don't know what the best current known bounds are. They're in Penrose's book. But I doubt that just doing coupling you'll find the exact value. But it's constant, yeah.
What's the threshold for containing a triangle?
For containing a triangle, it's much earlier than well, much earlier. It happens the first time when you see components of size 3. So because very much in contrast to GNP random graphs, the most likely component, when you have a component of size 3, the most likely to have them actually well, you have the points very close to each other. So whenever you can find 3 points so close that you will find a component of size 3 already, you already have a triangle. So you just have to compute the radius. It's far below, because this graph is not like a, so this graph is locally much dense. So you might have, for example, 4 points here and 4 points here and 4 points here, and the graph is still far from being connected. You don't see in an Erdős-Rényi graph a clique of size 4 at the connectivity threshold. You have to wait way longer to see this. But in a random geometric graph, it's relatively easy to have 3 or 4 or 100 points close to each other, and you can compute it. It's just the probability that you have basically a component of size 3 or 4.